Hi there, and welcome to another episode in the Geology 101 Physical Geology video series. I'm Geology Professor Shawn Willsey. This video series is just like my physical geology course I teach here at the college. Same curriculum, same content. You're just missing some of the labs and field trips, which you can somewhat supplement with some of the other videos I have here on my YouTube channel. Thanks for joining me today. Today in episode 35, we're going to look at different landforms created by rivers and streams, talk a bit about floods, and kind of piggyback on what we covered in episode 34. So if you haven't watched episode 34, make sure you watch that one first, where we talk about velocity, gradient, more of the dynamics and characteristics of streams. Before you watch this one, I think it'll make a lot more sense. So let's go ahead and get to it here. So the river is obviously moving. It is an energetic entity, and with the velocity and the energy and the volume of water that the stream carries, of course, it's able to transport sediment. That's sort of the main job, I suppose, of the river or stream, is to transport sediment. And it does that in a couple of different ways. It can either carry fine particles in suspension, like basically in the water column itself, and that's what we call the suspended load. And then the larger particles that it can't quite carry in suspension, it just drags those across the bed of the stream. Maybe they're rolling, maybe they're skipping and bouncing along the bed of the stream, and that's called bed load. Now, the size of the particles depends a lot on the volume of water in the stream, the gradient, the discharge. All those things are important and will dictate to some degree the size of the sediment. It might be just clay-sized particles in the suspended load with sand on the bottom as the bed load, or it could actually be sand that's carried as the suspended load in a more energetic stream, and larger gravel-sized particles in the bed load. I'm going to show you here just a little example of that. I have a fun little tube here. And this tube has obviously water in it, but it also has sand and gravel. And so if I give this velocity and shake it up, I don't know if you can hear the gravel moving around in there, I can transport all the material. But as I start to slow it down, the gravel and the sand settle out really quickly. They've already been deposited as I stopped moving the little tube here. And now you can see this murky water up here. This is the suspended load. And over time, that suspended load, if I let this just sit on my desk for an hour or two, that suspended load will settle out and be deposited as well. So just a simple example of how that works with the suspended load and the bed load. So that is the work of the stream, is to transport the sediment. Just some pictures here to show you how this might look. Here's a river in flood stage, the Elbow River in Washington. You can see a big log right here, and you can see just how murky that water looks. It looks like chocolate milk, maybe tomato soup, but that is a river at high flood stage carrying a tremendous amount of material as suspended load. The water is no longer clear or transparent. It's quite murky, and that would be a good example of suspended load. Then this bottom left photo here shows these large particles, these gravels and cobbles here on and near the bed of the stream. This is the bed load. Now, right now, they're not moving because the river's at a fairly low flow there. But you can imagine when we increase the velocity, increase the discharge during a flooding event, that we could attain enough force from the water itself to cause these rocks to flip over, to roll, to bounce, to collide with each other. That, of course, will allow them to become more rounded. They're not going to get picked up and carried by the water in the water column per se, but they're going to get dragged and moved along the bottom, and that's a good example of bed load. Now, when we talk about streams, we can also talk about their ability to carry sediment as both a volume and a size. And so these are two characteristics we often look at with streams, and that is their capacity and their competence or competency. So the capacity would just be how much sediment the stream can carry, so the volume of sediment that the stream can carry. And this is going to be determined by the discharge. Larger discharge rivers that carry more water can move and transport a greater load of sediment to their base level, to their mouth, where they'll then deposit and dump most of that sediment. And the other way we can look at streams is their competence. So basically, what's the largest size particle, rock, if you will, that a stream can transport. And that's going to be a function more of its velocity. So you can imagine standing by the banks of a stream that's moving by at a fairly good clip. And let's say you start with a small little pebble, and you throw that in the stream, and if it's, let's say the water is really clear, you can see to the bottom, and you notice that as soon as it hits the water, or as soon as that rock hits the water moves it downstream. But let's go to a bigger, and you select bigger and larger size rocks over time. Eventually you get to a size where it moves but just barely, and if you go to a larger particle, it just sits there on the bottom. It does not get transported by the river based on the velocity of that particular moment. And so that would be capturing the competence of the stream. Well, it's the biggest rock size that you can move. And of course, floods actually increase both of these parameters. So when we have floods, we have more volume of water, we have greater velocity, and so we can increase the capacity and the competence or competency. The sediment that the stream carries, we often call this stuff alluvium. It might be large particles like in the photo here. It could be finer sized particles, depends on the stream's characteristics. But it's a fun word to know, I suppose, because you might be looking at property that you're looking to buy, and you notice that your property on a geologic map sits on an area of alluvium. So the next question I would have is, well, where is the stream that deposited that alluvium? Maybe it was millions of years ago and the river's not even in that landscape anymore. Maybe the stream is nearby, and if it deposited that alluvium there at one point, is it possible that it could deposit that material again? Maybe you're up on a terrace, maybe you're down by the water. But usually when we see floods and high discharge events, the velocity tends to drop, the sediment gets deposited. Sometimes that's on the channel or the bed of the stream, sometimes it's on the banks of the stream, sometimes it's across a large valley, we'll talk about that in a second, like a floodplain, or it could be at the mouth of the stream where it ends at a valley or an ocean or a lake. But regardless, if it's sediment transported by water, moving water, it is called alluvium. So this is a slide from the last episode. You might remember this from episode 34. And in episode 34, we talked about the movement of water down a channel and where the velocity is high along the outside bend of a meander or a bend in the stream, and where the velocity is low. And that's kind of where we ended that episode. We didn't go much further than that, but now we're actually going to give a name to these landform features. We're going to look at several different types of stream landforms that are often quite common. And so this area on the outside of the bend where the velocity is higher, the stream is moving faster, and it's actually eroding or cutting into its banks over here. This is what's known as a cut bank. So this is what's known as the cut bank of the stream. There's even a town in Montana called Cut Bank, Montana. And over on the other side of the stream where we have lower velocity on the inside of this meander or bend, this is what's called the point bar. So the point bar is an area of sediment deposition. Sediment is being dropped and deposited here. And so this is what's known as a point bar. Again, erosion on this side, deposition on this side. If you think about how this landscape might change over time, well, if the river is cutting into its banks over here to form this cut bank, that means that over time, this stream meander, the actual position of this bend in the river over time is going to change, and it's going to shift more into this direction. So we might see in the future that the meander has moved or migrated or cut in this direction, and that we might see the edge of that meander over here at some point in time. Of course, it should stand to reason that if the cut bank and the meander moves in this direction, then the point bar will move with it. So the point bar will actually move in that direction as well. So the whole river channel is shifting across the landscape dynamically over time. So rivers are incredibly dynamic entities. They move on human timescales quite easily. So we can also see in a steeper, more rugged landscape like the Grand Canyon, you can start to pick out these features still as well. You can see the main current here going down the left side of the stream. The stream's flowing away from us in this view. So you can see where the stream is flowing. This would have the highest velocity over here. This is where in a big valley it would be cutting into the landscape, but these are hard resistant rocks, so it's not cutting as quickly. But what we can see on the opposite side, where the inside of the bend of the stream is, we can see another point bar, and the point bar here has actually gravels and sand on it. So point bars need not always be one specific sediment type. In a more energetic, steeper river, you might see gravels and larger sediment sizes that make up that point bar. Other landforms we find in these types of settings would be things like floodplains. So here is a stream meandering across this region. You can see it's a little bit hilly down here, a little bit hilly over here, going up to some higher topography. But this area, which gets flooded, whenever the river floods, it spills out over its banks, it inundates this area, and each time it does it, it deposits some of that suspended load. Those fine sediment sizes get deposited on the landscape, and it creates this flat region adjacent to the stream that we call a floodplain. Now, somewhere in the course of human civilization, we forgot this one basic fact: floodplains flood, and it's no, it makes sense why humans would have settled these areas. It's close to rivers, which were a source of water and transportation, good soils for growing crops, but nonetheless, floodplains do flood over time, and so that's why they merit a certain amount of caution as a hazard. So these are floodplains. Other stream landforms that are pretty common are things like deltas. So here you can see this stream flowing down into this body of water, this lake here, and you can see that the river has deposited over time this somewhat triangular shaped deposit here, and this is what's known as a delta. And so you can see the river is actively flowing in this region here. You can actually see the channel here, some of the suspended load, different color as it hits this very beautiful water here. You can see where the stream has flowed in the past, but as the stream flows down, it actually is depositing material along its bed, along the bottom of the stream, and that builds up the bottom of the stream to the point where at some point the river moves from that channel into some other channel. Now, it looks like it's been moving in this area recently, but it also could move into this region. It moved there once in the past. That's why there's land there, and the river could eventually, what we call a grade, build up sediment in this area and migrate into some lower area over here and start flowing in this direction. So, if I was looking to build a house somewhere in this landscape, I definitely would not build on the delta. Even if you, even taking out the worry of a flood and a high discharge event, just the river flowing, at a constant discharge, it's depositing sediment in this channel. It's going to eventually abandon this channel and select some new pathway for it to flow. But this buildup of sediment here is what's known as a delta. We get similar features in drier, more arid regions like deserts, where a stream comes down out of some higher relief area like the mountains here. This is down in Death Valley, and then it enters this big flat landscape. This is one of the big dry lake beds, the playas there in Death Valley, and as it comes down to this flat landscape, it immediately loses a lot of its velocity. The gradient goes to zero, and so it deposits this big fan-shaped bit of material here. This is all sand, gravel, and maybe a little bit of clay on the landscape. You can actually see the road here coming around the edge of this this alluvial fan. And then let's go down to road level so we can see the different slopes, because we have three different topographic features here. We have the steep mountains there, we have this less steep alluvial fan, and then we have the valley floor here, which I suppose is best seen down here in the bottom left, or the left edge of the photo, where you can see some of the salt and mud deposits there. And this would of course be fairly flat. So if we go down to street level, we can see the road here, we can see the steep mountain front, we can see the flat valley floor of the playa here in Badwater Basin, and then we can see the alluvial fan itself. So hopefully you can see those almost three different slopes, if you will. The slope of the mountain front, the slope of the alluvial fan, and then the flat, nearly horizontal slope there of the basin itself. So when we look at streams, we have different landscapes that streams form. Of course, valleys and canyons are one of those types of topographic features. So some streams that are very young, or they're starting out in a landscape where they're down cutting, the area maybe is being uplifted. So for example, the Yellowstone River here, this is the Grand Canyon of the Yellowstone, a very young landscape, and you can see we have a fairly straight stream. There's a few little bends in the river, but it's in a very tight V-shaped valley. There's no floodplain whatsoever. There's no large meanders to the stream. It's quite narrow. It has sometimes have waterfalls on it. It might have rapids and whitewater. This indicates this is a very young, youthful stream system. But over time, as the water starts to meander back and forth across, cutting into the walls of the canyon, it's going to take this very rugged landscape and make it a little more subdued. The canyon is going to get wider over time. That will allow the stream more area to meander back and forth. Waterfalls and other steep features will become less so, and this landscape will become more open and more wide. It takes quite a bit of time, obviously, over geologic periods, but eventually we might have more of like a wide valley. And so this boring slide with some words here, hang with me here and I'll get you to a nice graphic here in a second. So we've talked about the floodplain, the meandering stream back and forth, carving out and creating this big wide flat area adjacent to the stream. We've talked about the cut banks and the point bars, depending on where the current is fastest and where it's slowest. Over time, those meanders can actually get cut off and the stream can create a shortcut. I'll show you an image of that here in a second that'll make sense. And those abandoned meanders, if they're filled with water, those are sometimes what we call oxbow lakes. They kind of look like the harness that pioneers used to put on their oxen as they were pulling their carts and such. And if they're left dry and not filled with water, they're sometimes called meander scars. And so here is a Google Earth image of the Nowitna River in Alaska. So you can see this stream meandering across this landscape. The point bars show up very nicely, these lighter colored deposits of sediment on the inside bend of the meanders. Excuse me. And we can see places where, remember, the river flows fastest around the outside of the bend. Here's one in particular that looks like it's sort of evolving. So if the river's flowing faster around this outside bend, and maybe it's not even, moving so fast here, but eventually this little neck of land will get thinner and thinner and thinner, and eventually the river will breach that spot, take a new path, completely abandon this channel over here, and create a new path for itself. And when it abandons that old meander, that's what we call an oxbow lake, if those are still filled with water. And I pointed out one here, but there's a bit of one over here. There's a great one down here, a little bit of one here at the bottom edge of the photo. You can just see several of these. You can also see places where they're no longer filled with water, but you can actually see where the river used to flow across the landscape. So these are these meander scars. This one here is almost a little bit of both. It's got water on the left side here, and it looks like it's a little drier here on the right side. So a bit of a meander scar there. So incredibly dynamic, these streams, and incredibly impressive landforms. I invite you to just get on Google Earth and just find a river or stream, just zoom in, check out the different features, and you can learn a lot by doing that. You can learn a lot about river dynamics and how things look over time. I want to end this episode by talking just briefly about floods. We could spend a whole another episode on floods, flash floods, different aspects of flood systems, but let's just end with floods just briefly. So this is the most common and destructive of all the hazards, more than earthquakes and volcanoes. At least year in and year out, floods happen more often than anything else. They happen, I think, in virtually every country, every continent. They're incredibly common across multiple landscapes. And the reason we get floods is pretty complicated, but it usually boils down to several factors. So it might be heavy precipitation. That's probably the most common one. You just put too much water onto the landscape very quickly. It could be maybe the remnants of a hurricane or a tropical storm. It could just be a heavy rainstorm event, a prolonged rainstorm that just kind of sits over an area for some period of time. How saturated the ground is will dictate how big the flood is. So if the ground is quite dry, you might be able to absorb a lot of that initial rainfall or snow and not really get as bad of a flood, or maybe no flood, depending on the situation. But once the ground is saturated, the water can't absorb or hold any more water, so it starts flowing along the surface, and that really sets the stage for these flooding events. The topography is very important. How quickly water is moving from high elevation to low elevation. Is it steep topography? Is it more subdued? How big are the drainage areas that the individual river and stream systems have? Do they drain large areas or small areas? That will dictate how much water can be in that particular system. And then sometimes we get actually things like dam failures. We could get natural dams. I don't mean like beaver dams, but things like landslide dams that, landslides go down into a river, dam up the river, and you can get those types of failures. Might be like in the Western Grand Canyon, there's actually lava dams where volcanic eruptions have taken place. Lava has poured into the canyon, dammed up the canyon, and then later you can get those breaching. Or it could be man-made dam failures. Here in Idaho in the late 70s, there was a historic catastrophic collapse of the Teton Dam that was very much a high impact event to the areas downstream. So just a few examples there of different types of flood events there. So that is our episode here, wrapping up the section on rivers and streams. And thanks for joining me, and we'll see you in another episode. Take care.